I think that works.
This is fine.
So this is okay. So they say every talk is a job talk, but fortunately this one's just a practice. So I don't need to be that worried about it, right? So I plan to use my time to show you how I answer my overall research question of what were the processes whereby our Earth evolved to its present state. I work in broad field of geophysics, and I seek opportunities to connect the different disciplines with my primary area of research, which is seismology. Today, I'll specifically speak about how seismology, combined with mineral physics and geodynamics, can tell us about how the inner core grows and powers our planet. Understanding the behavior of Earth's interior is fundamental to understanding the processes operating on the surface. And while from my talk title you may think this talk is entirely focused on the deepest part of the Earth, this talk builds on some crucial insights from my work on the structure of the Alaskan subduction zone, which I'll also mention here. The inner core is a fascinating part, as despite being less than 1% of the volume of the whole Earth, and being buried over 5,000 kilometers down, it has, its structure and growth have profound implications for the rest of the planet and its habitability. It's almost pure iron at 300 gigapascals pressure and 5,000 degrees Kelvin, which is just a little bit less than the temperature of the surface of the sun. The inner core at the very center of the Earth is likely the present-day source of the energy for Earth's outermost layer, the magnetosphere. And it's the magnetosphere which shields the Earth from the charged particles in the solar wind. The Earth's magnetic field results from movements of liquid iron in the outer core, and it's most likely that the inner core is growing from the center out as the outer core cools and freezes, like a snowball adding new layers. Since the nucleation of the inner core, the latent heat of crystallization and the release of buoyancy and form of light elements has contributed to the outer core energy budget, and thus it powers the geodynamo. The distribution and the release of buoyancy to the outer core affects the power of convection, and thus the generation of the magnetic field. Understanding the history and growth of the inner core is thus crucial to understanding how the magnetic field is grown. And the structure of the inner core will likely record this growth history, and we can use seismology to see this. There are several different ways that we can look at the properties of the inner core. We can measure the seismic wave speed, the density, and elastic properties. There are different methods that we can use. First, we have waves that propagate through the Earth, known as body waves. These are of the highest frequency and have the highest spatial sensitivity. But they are only sensitive to the area of the region of the Earth immediately around the ray path. And so it's limited by source and receiver distribution. So we have relatively or poorer spatial sampling through body waves. Next, there are normal modes, which are whole oscillations, or full oscillations of the whole Earth. These are much lower frequency and so have lower spatial sampling, spatial resolution, but tell us about the whole Earth. However, with all normal modes, their sensitivity goes to 0 at the center of the Earth, and so they can only really tell us about the shallower structure in the inner core. And then finally, if we were to cross-correlate noise records, we can pick out recurrent signals relating to paths traveling through the deep Earth. Because this is just using ambient noise, which we can assume to be globally distributed, we can make these measurements wherever we have stations. So this dramatically increases the amount of sampling, or how well we can sample the Earth. However, it's complicated to make these measurements, and it's also very complicated to work out where in the Earth these waves are actually sampling. So since the discovery of the inner core by Inge Lehmann in 1936, seismic study has revealed increasing complexity in inner core structure, both laterally and in terms of depth. And this figure summarizes the details of the inner core structure that has been discovered to date using a variety of the different methods I've just introduced. This is a cross-section through the inner core in the plane of the rotation axis. And to begin with, just in the outermost part of the inner core, we see isotropic velocity differences in two different hemispheres. The eastern hemisphere is seismically fast, and the western hemisphere is seismically slow. And this layer is thicker in the eastern than it is in the western hemisphere. There is a very sharp transition between east and west hemispheres on the order of a few degrees of longitude, although some work that I'm just doing at the moment kind of disputes this, but I won't talk about that anymore.
Where do you western and eastern Greenwich mean?
So the hemispheres are not quite the same, but are very similar to geographic hemispheres. It's depends on which model you're taking. It's somewhere between the eastern boundary of the eastern hemisphere is either Greenwich meridian, or maybe 40 degrees to the east of Greenwich meridian, and then the western boundary is somewhere between about minus 170 degrees longitude and minus 160 degrees longitude. Depends on the model. So you can refer to them as hemispheres, or you can refer to them as quasi-hemispheres, and depends on the data set you're using to determine. And then below this layer, below the layer of isotropic velocities, the bulk of the inner core shows anisotropy, where waves propagating in, parallel to the rotation axis travel faster than those propagating in the plane of the equator. And this also shows hemisphericity, although it's the opposite of the shallow hemispheres. Here, the western hemisphere shows stronger anisotropy than the eastern hemisphere does. There are even suggestions of another deeper layer, an innermost inner core, although work that I published earlier this year doesn't find any evidence of innermost inner core at all. Today, I will talk about anisotropy in the inner core and my model of the structure of the deepest part of the inner core. So what is seismic anisotropy, and why do we want to measure it? Anisotropy is a described materials where the properties depend on the direction. In this case, the speed of seismic waves depends on the direction that wave propagates. For example, the upper mantle mineral olivine transmits waves faster along its crystallographic C axis than it does its crystallographic A axis. And this is on the scale of a single crystal, and it results from the specific crystal structure of this mineral of olivine, and so it's referred to as intrinsic anisotropy. Alternatively, collections of multiple crystals, such as rocks, can develop can be made anisotropic by deformation. What can anisotropy on the scale of the core tell us? Large-scale anisotropy can be interpreted as some kind of alignment of objects with different wave speeds. We can either have, this can either result from alignment of objects with a preferred shape, known as shape-preferred orientation, or else alignment of, preferred alignment of multiple intrinsically anisotropic single crystals, known as lattice-preferred orientation, also known as crystallographic preferred orientation. And we can use this anisotropy of the Earth to tell us something about the crystal structure in the inner core by inferring which phase of iron might be stable. In addition, large-scale anisotropy requires a mechanism of generating alignment on, through deformation. And so, by observing anisotropy, which is evidence of accumulated deformation, it may tell us how the inner core grows and develops. And when and how the inner core crystallized will have implications for the power source of the geodynamo. In this talk, I will address several questions about the inner core, starting with trying to work out where in the Earth these seismic anomalies are coming from, and whether we can actually attribute them to the inner core. Next, I will assess the distribution of anisotropy within the inner core. And finally, I will connect my work in seismology with other disciplines, namely mineral physics and geodynamics, in an attempt to work out how the inner core behaves. To identify patterns of seismic phenomena with velocity anomalies, I measure the travel time of body waves which sample the core. Specifically, I use the core waves PKP, which comprise the outer core branches PKP, AB, and BC, and the inner core branch PKPDF. I calculate the travel time anomaly of the wave sensitive to the inner core, PKPDF, relative to a 1D reference. And then to account for the heterogeneous velocity structure outside of the inner core, I calculate the differential travel time between the inner core phase, PKPDF, and one of the outer core phases, either PKP, AB, or BC. Sorry?
What is the predicted PDK?
So we use a 1D reference model. We use a 1D reference model of the velocity structure through the Earth.
Which reference?
So I'm using AK-135. This is the one that's best parameterized for inner core structure. So we could use PREM, we could use IS-291. I use AK-135. And so we make our observations relative to this reference. And the reason for doing the differential is that we look at where it's similar. For these two phases, an outer core phase and an inner core phase, or the inner core phase, they have relatively similar paths in the crust and mantle. But only the DF wave is sensitive to the inner core. So if we calculate the difference of the two relative travel time anomalies, we get the differential travel time anomaly, which should just tell us about the part of the path that is distinct, which is the inner core. The path of PKP-BC is more similar to that, sorry, BC in purple, is more similar to DF than AB is. And so we assume that because they're traveling through more similar material, the BC minus DF differential travel time will be the most reliable, will best correct for crustal and mantle structure. But because of geometry, we're often limited in where we can measure this. We can see PKP BC at a relatively short range of distances before it's obscured by the inner core, whereas we can observe PKP AB out to a larger range of distances. So even though it's likely more contaminated, if we want to look deeper into the Earth, we have to rely on this AB minus DF measurement. And in this example, we see that the PKP-DF wave arrives about 8 seconds prior to the time predicted by the 1D reference model. In contrast, the AB phase arrives at the time that's predicted by the 1D reference model. So the residual travel time tells us that DF is fast compared with the reference. And then the differential travel time tells us that this fast velocity anomaly is in the inner core. And we characterize these paths by the angle, xi, which is the angle that the inner core portion of the path makes with the rotation axis, ranging from 0 degrees for paths parallel to the rotation axis to 90 degrees for paths in the plane of the equator. And the interior of the inner core has been shown to be anisotropic, with travel time anomalies depending on xi. This is parameterized as transverse isotropy, or cylindrical anisotropy, where the velocity anomaly depends only on this value xi. Depends on this value xi. This parameterization simplifies the equation of anisotropy to a function of cosines and sines, cosine squared and sine squared. It's only dependent on 3 parameters and xi, which is really handy given that anisotropy can have 81 independent parameters. And so this travel time anomaly depends on xi. Xi angles below about 35 degrees are referred to as polar, and greater than 35 degrees are referred to as equatorial. Waves near parallel to the rotation axis travel several seconds faster than those in the plane of the equator. Furthermore, polar data have demonstrated hemispherically distinct anisotropy, with stronger anisotropy in the western than the eastern hemisphere. Here I'm showing the travel time anomaly plotted at the ray turning point on top of the inner core portion of the path. And you can see how it changes from faster to slower from out of the west to the eastern hemisphere. This is just for one particular past study. However, all past studies have been unable to fully characterize the pattern of anisotropy due to limited data at the most polar angles. Moreover, to date, the majority of the polar data has come from this particular path from earthquakes in the South Sandwich Islands, observed at stations in Alaska. And from these data, models of inner core anisotropy have been developed, such as this black line. This black line, which is the model, fits the data relatively well for the more equatorial data, but has to miss this part of the data in order to match the most anisotropic data. And this most anisotropic data is from the South Sandwich Islands to Alaska path. And then at the more polar angles, the pattern of anisotropy is polarly constrained, very polarly constrained. To counter this, I took advantage of some recent temporary deployments in Antarctica and also the expanding US array in Alaska. From this, I was able to make new polar measurements. In our data set, we have good global distribution, and most importantly, a lot of our polar paths, our polar observations, come from paths that are independent of the South Sandwich Islands to Alaska path. Specifically, from a few high-latitude earthquakes observed at stations in Antarctica.
Dan, can you use waves that are reflected? So P, K, D, K, P, K, D, K, P.
We simplify that
Same
to
confidence.
P prime, but yes. So, so yes, exactly. We can use reflected phases. And, in one of my previous studies, I did use reflected phases. They're a little bit harder to spot because they're
Yeah,
probably-
which is way slower.
Yes, but you can still use them, and they are another way of finding independent data. So all the ways we can find of getting independent data are really valuable when we're trying to avoid certain paths that we think might be contaminated. But yeah, reflected phases are very valuable as well, just not as well studied. So as I showed in the example, I measured the differential travel times by hand for about 5,000 earthquake station pairs. And I characterized the observations by the clarity of the measurement relative to the noise. And in the end, I have about 2,200 and 1,600 AB minus DF and BC minus DF measurements respectively for the highest quality data, which I'm plotting. Well, I'm plotting the AB measurements here. I'm showing the differential travel times for only the best quality data, showing travel time as a function of xi angle. And we see the pattern of anisotropy, which is fit by this green line. In this data, we find that the fastest travel times are along the rotation axis, close to the rotation axis, and the slowest are at about 60 degrees relative to the rotation axis. There's a lot of information in this figure, and I'm going to start unpacking it to try and answer some of my questions. To begin with, where in the Earth is this travel time anomaly actually coming from? Is it coming from the inner core? So here I'm showing the same data as before, but now I've colored the data observed at stations in Antarctica in green. Sorry, stations in Alaska in green. And observations from earthquakes in Alaska observed at stations in Antarctica in purple. I'm also showing a new anisotropy curve calculated by excluding the green data. You can see it requires much less anisotropy. The green data covers a very large range of travel time anomalies over a relatively small range in xi angle, suggesting that this pattern is not actually dependent on xi at all. Meanwhile, the data from earthquakes in Alaska do better fit the global pattern.
Dan, where did the data come from at the very, very low angles and very, very high anomalies?
These? So these are from those few earthquakes I mentioned that are in Jan Mayen Island, north of Iceland, north of Greenland, observed at stations in Antarctica. So that's almost antipodal, so these are very deep, and they're very close to the rotation axis. And yes, there's a lot of scatter there, and I'll talk about that in a minute. So as I mentioned before, the AB minus DF measurement is more prone to contamination because the paths are more separate than BC minus DF is. So we assume the BC minus DF measurement to better correct for the mantle and crustal structure. However, when we just look at the BC minus DF data, we find the same pattern again. The data observed at stations in Alaska sticks up and does not match the rest of the data, the rest of the global data. In addition, the range of travel time anomalies for both of these phases is about the same, even though the AB minus DF data are observed at much greater source receiver distances, which would, when the DF phase is going through much more of the inner core, so we expect to be more affected by the inner core. This implies that this pattern isn't coming from the inner core. At the same time, the amount of time that AB and BC spend in the crust and mantle is about the same for all source receiver distances. So this is pointing away from the inner core for the source of these anomalies. But whatever is causing these discrepancies has to be unique to the South Sandwich Islands to Alaska path, and has to be very strong and spatially sharp to be able to sharpen the differential measure. It has to be able to affect one of these paths and not the other path. The differential measure is assumed to account for the upper mantle structure, but 3D ray tracing and waveform modeling in regions of strong heterogeneity, such as slabs, has shown that even small differences in propagation angle of the wave relative to some heterogeneity would lead to large differences in travel time anomaly on the order of several seconds. In this 3D ray tracing example, we can see that waves are 3D ray tracing waves in green are affected, the trajectory is affected by this high velocity structure. It acts as a waveguide and pulls the waves away from the 1D theoretical path. And this also manifests as travel time anomalies. But in addition, so we need to be very careful when making measurements around subduction zones. But in addition to the travel time anomaly, if you look closely, you'll notice that the angle that these green paths are coming into the receivers at is different from the 1D prediction, from the black line. So this ray path directional anomaly points to a possible way of identifying this contamination. Alaska provides an excellent environment to test the effects of strong upper mantle structure on deeper traveling waves. The Pacific plate subducts under the North American plate and has varied subduction behavior with shallow and steeply subducting slabs and also subducting microplate. And all of this is related to the complicated tectonics of the Alaskan region. With Steve Roker at Rensselaer Polytechnic Institution, we have revisited the structure of the Alaskan slab, and we are producing new P-wave and S-wave holographic models of Alaska using body wave travel time data and 3D ray tracing. We're finding very strong lateral and vertical seismic velocity variations around the Alaskan slab and the Yakutat terrain. And we currently resolve this down to 400 kilometers depth, but we have a proposal currently in review to use waveform modeling to image this more accurately and more precisely and also deeper into the Earth. But the strong and sharply varying velocity variations that we see could contribute to the travel time anomalies that I mentioned. And with single stations alone, we can record the PKP travel times. But with multiple stations together, as we have in Alaska, we can use array processing to resolve PKP directional anomalies. As a wavefront moves across an array, the delay time of the station, the delay time of the wave at each station in the array tells us which direction the wave is coming from. And this can be measured in terms of angle on the surface, or back azimuth, which we usually measure relative to north, and also incidence angle, the inverse of which is called the slowness, or close equivalent to the slowness. And so this is the steepness of the wave coming up. This is measured in seconds per degree. Using the information of back-azimuth, slowness, and travel time, we can work out the direction and the incoming trajectory of the wave. Recall that strong velocity variations can bend waves off of predicted paths and also affect their travel times. And using this method, we can measure the observed direction and travel time. And using our tomographic model of Alaska, we can 3D ray trace to predict what directional anomalies the slab would cause. So we form subarrays of the US array, each of which contains up to 9 stations. This example is from southern Alaska around the Cook Inlet. And we observe the different PKP branches have different move-outs depending on the velocity structure. We can see the 3 predicted arrivals in purple, but PKPDF arrives earlier than is predicted, and with a different move-out, a different slope than that which is predicted. So PKPDF is coming in from a different direction than the 1D model will predict. We can perform beamforming to test the best fitting direction using a grid search approach. Here in slowness space, PKPDF picked by this picked at this blue point arrives at a different slowness, higher slowness than is predicted, shown by the purple. Meanwhile, PKPBC arrives at the slowness that is predicted. Then in back-azimuth space, PKPDF arrives at a distinctly different back-azimuth that is predicted, whereas BC arrives at the slowness back-azimuth that is predicted. So PKPDF is being strongly affected by something, while PKPDC isn't. We repeat this subarray approach across the whole of Alaska. We measure travel time, slowness, and back-azimuth anomalies for PKPDF for subarrays across Alaska for 6 different South Sandwich Islands to Alaska events. Here I'm showing the average of those measurements across the 6 different events. We find some very interesting patterns that are systematic in space and robust across those 6 events. First, travel times, we see a region of early travel times surrounded by later travel times. Then in back-azimuth, we see a very sharp change from negative slownesses sharply changing to positive slownesses. And then in back-azimuth, we see negative back-azimuth anomalies surrounded by positive back-azimuth anomalies. We then turn to our tomographic model and draw a contour around the Alaskan slab at 200 kilometers depth. And this black outline also shown here shows a lot of similarity in location to the trends I've just been talking about. We can then use a 3D ray tracer to predict the travel time, slowness, and back-azimuth anomalies that would result at these same subarrays across Alaska. We measure the move out of the rays to each station of the array, and we calculate the incoming wave direction. Bear in mind that in these predictions here, the only velocity structure that I've introduced is 400 kilometers of upper mantle in Alaska, with a 1D model everywhere else. Even so, we're able to match a lot of these patterns that I've just mentioned. Early arrivals, early travel times over the slab, negative arrivals everywhere else. Sharp contrast from negative slownesses to positive slownesses, and negative back-azimuths surrounded by positive back-azimuths. And it's a lot easier to see these correlations when we look at these in an XY plot. What's noticeable is that the back-azimuths do have a lot larger scatter than any other measurement, but then that's to be expected because PKPDF back-azimuths are very sensitive to small changes. Even so, the trend is well matched. But then for the travel time and slowness, we really do well match the observations, just using, as I said, 400 kilometers of Alaskan mountain. Yep.
But Dan, the slopes to me don't look that close to 1.
No, they don't. So the fact, especially the travel time, the fact that the travel time slope is less than 1 is telling us that the velocities in our model are not strong enough. The trend is very well matched, so the trend of the anomaly is good, but the strength of the anomaly is not enough. I've done some synthetic tests where I've taken the tomographic model and just arbitrarily amplified bits of it, and I get a better match. But it does tell us that we really need to go back, and hopefully we will do in our new proposal, and update the velocity structure in the Alaskan mountain. There are lots of sources of discrepancy. Yeah.
So is that just saying kind of the geometry of the tomography model is correct, just damping or something, right?
Damping is most likely one of the problems.
I guess the spatial geometry is kind of, as you said, providing instruction.
Yeah. So the spatial structure where the Alaskan slab is and where the Yakutat terrain is and things like that seems to make sense. That seems to fit. And so, like I said, when you amplify various parts, you get closer to a one-to-one trend. But it's the amplitude that's missing. And so maybe through waveform modeling, which is what we're proposing to do, and also going deeper, we'll be better be able to match the amplitude in this anomaly. But this exercise strongly suggests that the PKPDF travel times in Alaska are being contaminated by the Alaskan slab. And so this raises questions about all data, all PKP data measured close to slabs, which is something that we're currently writing another proposal to investigate. In future, we should be able to correct for these anomalies and incorporate this data into the rest of the catalog. But for now, I'm just going to ignore this for the rest of the in-core investigation. Yeah?
What's the frequency band that you're using?
This is 0.5 to 2 hertz. So high frequency stuff. So getting a tomographic model to that scale is going to be hard work, but we're going to do what we can.
Dan, the selectiveness of the distortion, does that tell you that the disturbances must be local?
The what, sir?
I mean, are you able to convince yourself that the structure that's affecting your results isn't that local structure to one of your stations or the earthquakes?
Yes, I am convinced that it's relatively local. It's mantle structure. There will be other complications on top of that. There will be things below the scale of the model that we can't see, and there will be things outside of the model as well. But the dominant trends are, we're able to replicate the dominant trends in the data with this.
So I guess maybe a better way of asking the question would be, is there something in the data that tells you that it has to be local, it has to be scale?
Nothing else would be able to generate these directional trends as well as the travel time trends. It's been suggested before that this data is contaminated not by the upper mantle but by the lower mantle, core mantle bandwidth. But it wouldn't generate a systematic. It would be very hard for a lower mantle structure, core mantle bandwidth structure, to generate this kind of systematic pattern on the scale of Alaska. It's possible, but it's very challenging to do, especially the back-azimuth and slow zones. And so this follows on to my second question of how can the remaining anisotropic signal, or how is the remaining anisotropic signal distributed within the inner core? A purely axisymmetrically anisotropic Earth would show a smooth curve of anisotropy with small scatter resulting from measurement error. Removing the South Salmon Jones to Alaska data does remove some of the scatter, but there's still scatter remaining, especially at the more polar angles. This hints at other regional patterns that aren't just dependent upon Xi. Displaying the travel time anomaly as symbol color and plotted over the portion of the ray in the inner core, we see that the magnitude of the travel time anomaly depends on longitude. This is a pattern which has been observed before and attributed to the hemispherical dichotomy. The anisotropy in the western hemisphere is stronger and anisotropy in the eastern hemisphere is weaker. And when we split the data into these two hemispheres, it does begin to explain some of the scatter, but some scatter still remains. So if we just look at the most polar data, and now look at it not as a function of Xi, but as a function of source-receiver distance, we see trends of increasing travel time anomaly, linear trends, increasing travel time anomaly with depth in both hemispheres. So if you look at the increasing distance is equivalent to increasing depth. The further apart the source and receiver are, the deeper they sample into the inner core. And so some of this trend of increasing travel time normally with depth will result from increasing path length in the inner core. But when we normalize for this, effectively converting it to a velocity anomaly, we still end up with these patterns of increasing velocity anomaly in either hemisphere, telling us that the velocity anomaly in the inner core is increasing with depth. We can then unwrap this pattern about the rotation axis. So we can see the pattern of anisotropy continuous across the two hemispheres from west to east. The strongest anisotropy is observed deep in the western hemisphere. In contrast, at a similar epicentral distance, the eastern hemisphere anisotropy is a lot weaker. Here I'm just reflecting the blue trend about the rotation axis. We can achieve a smooth transition of anisotropy by extrapolating the gradient of the eastern hemisphere across into the western hemisphere. And this matches, intersects the western hemisphere trend, telling us the deepest anisotropy is in deep western hemisphere. The strongest anisotropy is in the deep western hemisphere.
Are the error bars 1 or 2 sigma?
One. So the data is suggesting that the strongest anisotropy is not in the center of the Earth. And so this brings us to how can we interpret these seismic observations in the context of Earth's composition and behavior. To do this, we can combine fluid mechanics models of inner-core growth with crystal scale models of anisotropy. I'll first go through my methodology before showing you the specific implementation. I begin by modeling flow of the inner core given some geodynamic growth model. I then calculate deformation within different parts of the Earth generated by that flow. And then I select the anisotropic properties of a single crystal of iron. And I start with a randomly oriented collection of single crystals, which we refer to as a polycrystal, and I calculate the effect of that deformation on that polycrystal, that initially randomly oriented polycrystal, and calculate the anisotropy that results at their location. And then I repeat this across the model under different local deformations to determine the global distribution of anisotropy in the inner core at the present day. I then test the ability of that model to, given growth model, and that given crystal structure, to reproduce the observations of anisotropy. And in subsequent slides, I will go through this method, and I'll use these cartoons as markers to guide you through the process. So I'm motivated to find a physical mechanism that can fit our observations. Several models of core evolution have been suggested. Taylor convection in the outer core would lead to preferential heat extraction at the equator, and thus preferential crystallization at the equator. This would lead to an oblate inner core, shown by the orange line, which I'm not very well tracking. Orange line. This would be gravitationally unstable, which would cause flow, degree 2 flow, in from the equator and up towards the poles. The little black arrows are showing the boundary, the internal flow. This would generate flow that is cylindrically symmetric about the rotation axis, with the strongest deformation in the center. Meanwhile, asymmetric inner core growth would lead to, has also been suggested, this would lead to a one hemisphere crystallizing faster than the other. This would cause a degree 1 pattern of lateral translation with a cylindrically symmetric flow perpendicular to the rotation axis. And this would lead to an asymmetric inner core properties. Motivated by our observations, the strongest anisotropy is symmetric about the center of the inner core. I test a model that combines these two prior models. So our combined model of preferential equatorial growth and asymmetric growth would lead to flow in from the equator and up towards the poles. It is modified by lateral translation. So I will stress that in contrast with previous models, our lateral translation model is a slow lateral translation, which means that the lateral translation rate is slower than the crystallization rate. In some previously suggested models, the lateral translation rate was faster than crystallization, which would lead to crystallization on one side and melting on the other. Our model is just leads to differential crystallization, more crystallization on one side than on the other. We're now going to test to see if this geodynamically driven model can reproduce our seismic observations. We model a neutrally stratified inner core with no convection and no stable stratification. This is really important. So neutral density stratification is the only regime in which deformation can occur with depth in the inner core. If we had a slightly unstable density stratification, that would lead to a large-scale convection. But if we had stable stratification, that would inhibit any radial flow. Therefore, neutral stratification is the only regime in which this style of deformation is possible. And this drastically limits the parameter space that we have to search. Assuming neutral stratification allows us to write the complete analytical solution to the flow, and we impose boundary conditions consisting of a sum of preferential equatorial growth and asymmetrical growth. This model is self-consistent, and we calculate tracer paths and the strain rate from the start of the inner core growth up to the present day. We calculate the instantaneous and the accumulated deformation. We find a pattern of greater accumulated deformation in a column aligned with the rotation axis and offset from the rotation axis. We now consider the mineralogy of the inner core. Recent physics model experiments suggested the inner core comprises iron and hexagonal close-packed structure. And similar to olivine, HCP iron is intrinsically anisotropic, with a single crystal anisotropy of about 8%. Here we use iron-nickel alloy for reasons which I'll come to later. And this assumption is consistent with cosmochemical and seismological observations of the Earth. We have to define a deformation scheme for our chosen mineralogy. HCP iron can deform in a total 4 different ways on 24 different slip planes. And we performed tests and we found that the only scheme that can generate strong, large-scale anisotropy is slip on the pyramidal C+A planes, an example of which is shown here. So in our calculations, we allow slip on the C+A planes. We then modeled the deformation of a set of crystals along each tracer on these given slip planes in the presence of this strain field, using the viscoplastic self-consistent code, or VTSC. We calculate how a polycrystal would generate texture given a strain field and the properties of a single crystal. We start with a polycrystal comprising 1,000 randomly oriented single crystals, and we expose it to the strain caused by this growth model. The more aligned the grains are, the less they look like random. Blue, like this, indicates that the grains are randomly oriented. After this polycrystal has been formed, we can see strong alignment of the crystals. If the single crystals in this polycrystal were all anisotropic, once they were aligned, they would look like one large single crystal, and so the whole thing would be anisotropic. In contrast, this polycrystal did not experience very much deformation, either because it was not in a particular, it did not align very much, either because it did not experience very much deformation, or the deformation it did experience was not unfavorable directions relative to those slip planes. Either way, this would not be particularly anisotropic, even if the single crystals in this were anisotropic. So in this model, we can summarize the anisotropy of these cartoons. Initially, randomly oriented with no anisotropy, partially oriented with some anisotropy after some deformation, and strongly aligned and strongly anisotropic after strong deformation. The result is thus the effect of the deformation of crystal texture integrated through time. And we construct a map of the cylindrical anisotropy in the inner core and find that for HCP iron, we can indeed produce strong anisotropy. We find that with a lateral translation rate of 0.4 inner core radii over the age of the inner core, we get the strongest anisotropy to be the offset 400 kilometers from the western hemisphere, so from the rotation axis. And with an inner core age of 0.4 billion years, we match the magnitude of the anisotropy. We compare the travel time anomalies predicted by this model, shown by the darker colors and the gray moving averages, with our observations, shown by the lighter colors and the black moving averages. And we find that this model well matches our observations in the data, both as a function of xi and as a function of distance. We match some of the really important features of this. For example, increasing anisotropy with depth in both hemispheres, an almost isotropic eastern hemisphere at the top, and stronger anisotropy in the west than in the east. And with this model, we get a variance reduction for the most polar data of 93%. We tested a range of different inner core ages and translation rates, and this is the one that's most likely. But then there are a few other elements that we need to test. I mentioned before of our assumption of an iron-nickel alloy for the composition of the core. We tried several different compositions and found that iron-nickel alloy best matched our data. We also tested pure iron. While pure iron has a very similar pattern of single crystal anisotropy, importantly, it is not as fast along the fast direction, and it is slower on the slow direction. And so when we repeat the prior experiment using iron as the composition of the inner core, we end up with a much poorer fit, 71% variance reduction for the data, and just it isn't capable of producing the same kind of anisotropy. So it's most likely that the inner core is not just pure iron. However, there is another caveat. Single crystal anisotropy is a function of pressure and temperature. And while the pressure range in the inner core is very small, at only 30 degrees, the temperature range is very small, at 30 degrees. The pressure range of 30 gigapascals has a larger effect on anisotropy. In our calculations, we neglect any effect of pressure and temperature, and we do that because there isn't enough data to allow us to do it properly. There are very few calculations for inner core materials at inner core pressures and temperatures. And so we do this extrapolation, but for pure iron, for which there is more data, but still this extrapolation is only pinned by 2 data points. But when we do the extrapolation for pressure across the inner core, we see that there is a pressure variation, that anisotropy does change from the top of the inner core to the center of the inner core. And so in our future work, we really do need to understand the effect of pressure on anisotropy. But back to our preferred model. This well fits PKP data, but also quantitatively explains all the other observations of the inner core that I mentioned at the very start of the talk. Our model fits normal mode observations of columnar anisotropy. It fits PK little IKP data of shallow hemispheres, and also fits P' data, which is the reflective phase, which shows weaker shallow hemispheres than deeper hemispheres. Future work will actually be to quantitatively assess these fits for our model to all the different data sets. I'm currently writing a proposal where we're using Bayesian inversion to resolve the inner core using all these different data sets at once. And so coming close to the end now, this model has some really important implications for disciplines outside of seismology. While we can't comment on mineralogical stability, in tests we find that body-centered cubic iron, BCC iron, just cannot produce the anisotropy that we see, that we observe seismically. So HCP iron is the most likely stable phase of iron in the core. Both from the regime diagram that we use and our tests on inner core age suggests that the inner core is likely younger than 1 million years. I'm not going to be that much more precise about that because assumptions in the mineral physics process will affect the age that we resolve. The inner core viscosity is likely greater than 10 to the 18 gigapascals, and the lateral translation of the inner core suggests the existence of some small thermal or buoyancy anomaly, density asymmetry in the outer core. And this model leaves some open questions. Can inner core anisotropy help us to constrain the light element in the core? What are the impacts of pressure and temperature on anisotropy of iron? Can we resolve the smaller scale dynamics of the inner core? And what do our observations tell us about outer core dynamics? And all of these are questions that I intend to answer in the future. And so, in conclusion, anisotropy in the inner core is dependent on location. The upper mantle structure does affect, or can affect, our observations of the inner core, and so we need to be really careful when making measurements in tectonically active regions of fusion. The maximum anisotropy is actually deep into the western hemisphere, demonstrating that the inner core is asymmetric. And our modeling suggests that the inner core could have grown by a combination of preferential equatorial growth and lateral translation. And this further supports the idea that HCP iron is the dominant form of iron in the inner core. The model fits all other seismic observations, and our model gives important constraints on inner core growth and outer core dynamics. And with that, I'll finish. Thank you very much. Bruce?
Dan, the age of the inner core, is that essentially set by requiring a neutrally stratified inner core?
So there are limits on the age of the inner core set by that, yes, set by that assumption. So that says it has to be greater than 0.2 and less than 1.4 billion years, based on convective timescales. But the precise age of 0.4 billion years comes from the effect that age has on the strain rate. So when we model this, we model a non-dimensional type, and then we scale it by some age. And so if we make the inner core younger, the strain rates are higher. If we make the inner core older, the strain rates are lower.
And you're modeling the temperature inside because the problem with growing the inner core too slow is, of course, it would be thermally stratified. So,
Yeah.
but the one question I really wanted to ask was, where's viscosity? Where's the constraint on viscosity?
So again, that's because of the model that we're choosing. Because we are talking about this Yoshida style convection, as we call it, it has to be within a certain viscosity range. So this is talking about, this is showing us the dominant deformation regime dependent on inner core age, non-dimensionalized here, or dimensionalized there, and viscosity. And the overlap, or the transition from this being the dominant regime to this being the dominant regime to convection being the dominant regime is at about 10 to the 18 Pascal
Stresses.
Sorry?
We need the stresses to be high.
Yeah. So we don't have an upper bound on that, but it's somewhere greater than 10 to the 18 gigapascals. Yeah, Harry?
Yeah, I just kind of wanted to follow up on that. So, how you did the flow calculation was a one step.
Yep.
And so, I wonder if you kind of had a time evolution of the flow and, allowed, say, viscosity to be anisotropic and isotropic. That would you expect that to kind of enhance the anisotropy signature? Because I know there have been some studies on mantle convection side that have allowed viscosity to evolve, but also be anisotropic. So that way.
So as far as I know, viscosity isn't a huge impact on this. What the precise viscosity is, we do use an isotropic viscosity. Yes, we don't change it. And I think if we did allow the viscosity to change, it would affect the result, but it would mostly affect the result at the inner core boundary at the very top, which actually is is important because that's where crystals are starting. That's where they are initially randomly oriented before they get oriented by the flow. So we would have some effect. We would have some modifying effect, but we don't know what yet. No.
When you talk about the indoor age, are you talking about through over that?
From nucleation to present day.
Do you have a rate that it's growing?
So I'm not sure what it is with these new calculations, but it's something like 800 tons per second, or 1 millimeter.
We'll just take the radius and divide it by the age as the
Yes.
first approximation.
Yeah. 1 millimeter a year, something like that. Yeah, so our model requires about 0.4 billion years to be the age of the unicorn. I'm aware that is lower than, or around the lower limit defined as suggested from geomagnetic studies. But I'm not fixed on that 0.4 billion years age. It's just the one that best fits our observations. Like I say, because of limitations or assumptions in how we do the mineral physics modeling, there is possible error on that. So if the mineral physics, if the grains deform more easily than they do, we don't know how grains deform in the inner core. If they deform more easily than they do in our model, then we wouldn't need as young an inner core to get the same kind of result. So the main range on the inner core age is this one. It has to be between 0.2 and 1.4 billion years. But we're saying more precisely around 0.4. 0.5 is fine too. If we go too high, go to 1 billion years age, then our model isn't capable of reproducing the strength of the anisotropy. If we go down to 0.2 billion years age, it is far too strong. Everything is anisotropic, which isn't what we observe. So there are some constraints, but they are fairly wide constraints on the age of the inner core.
And one last question is, the hemispheric differences show that the high wave speeds were correlated with strong attenuation, which is opposite of the thermal explanation we often use. Is that related to the compositions or light alloy elements?
So a fun future work would be to look at the effect of crystal orientation on attenuation, and also composition light elements on attenuation. The attenuation is something that hasn't been that well studied. It's been studied a little bit, but not that well studied. It's something that I intend to go back and redo, or do now we have a lot more data. But it will give some really important information about the crystallographic structure of the inner core. That is, if that attenuation signal is coming from the inner core, because that work was done before I started coming back and saying, well, actually, the upper mantle is affecting things too, and a slab can affect your attenuation. So it could be that the attenuation signal we're seeing is actually related to slab structures and not due to the inner core anyway. So an important caution on all of this work is whenever you're looking deep into the Earth, you really have to be aware of what's happening in the shallow Earth first. And you can't just go extrapolate, applying everything and saying everything is due to deep Earth. You really need to be aware of the shallow Earth first.
People sometimes attribute attenuation to grain size differences.
Yeah.
Okay, let's move our discussion to the conference room. Let's thank our speakers.